Okay, it's working. Okay, perfect. Thank you, James.
All right, thanks a lot, and see you soon.
See you. Okay, so we can start. Let me just open the slides and share my screen. Okay. Okay, you should be able now to see my screen. And yeah, and I'm recording. Good. So okay. So today we're gonna return back from the low energy gamma rays, so GV range, to high energies again. So Cherenkov astronomy. So detection of the detection of TV gamma rays. So 100 GV to several tens of TV. So, and I'm gonna speak about this peculiar instrument, which is named FACT, so which stands for First G-APD Cherenkov Telescope. So it detects gamma rays in the range of, well, more or less standard range for this type of instruments, 400 GV, 50 TV. So, and what's the specificity of this instrument is that it's using other alternative light sensors than the conventional Cherenkov telescope arrays. So usually Cherenkov telescopes use photomultiplier tubes. So photomultipliers, so these are light sensors. So the light is interacting with the photomultiplier, and the electron is ejected, and so it's ejecting more and more electrons on the way, and then the current is amplified, etc., etc. So here there is a different technology. So it's a novel, well, for that time, 2011, so novel technology, Geiger mode avalanche photodiodes, or shortened as G-APDs. So these light sensors are used in this instrument, and it's located on the Canary Island, La Palma, Spain. So maybe I can show you the location. So it's, yeah, so I zoom out so you can recognize. So this is the Canary Islands. And so the instrument is located next to MAGIC. So it's one of the Cherenkov telescope's major arrays. And so it's located just next to MAGIC array. So it's located over here. And so we can go back to slides. And so it's operational since October 2011, and the total field of view is 4.5 degrees standard. And another specificity is that it's a small single instrument. So usually a major Cherenkov telescope arrays are arranged into a configurations of, well, several telescopes. So array of 2 for MAGIC, or has 4 small telescopes and 1 large. So Veritas, I think 4 telescopes. So there are multiple, and these having several telescopes allows you to reconstruct the arrival direction of a gamma ray more precisely than for a standalone. So for a single telescope. So it's a single low-cost telescope, and it was built mainly for testing the technology of photodiodes. So G-APDs, but despite its modest size, it can be still useful to Cherenkov astronomy. So it's monitoring standard samples, like different objects. So standard sample is different TV blazars, so AGNs with the jet that is pointing towards observer. Also, of course, Crab Nebula, which is more or less standard candle. So it's used for calibration of instruments due to well-known flux properties. And okay, various other sources. I'm not going to really go into details. So now about the main core. So the main peculiarity of these instruments. So the G-APD camera. So instead of photomultiplier tubes. So this instrument uses Geiger mode avalanche photodiodes. So these are silicon-based photosensors, and their advantages are more stable gain, so, and higher photon detection efficiency than photomultipliers. So this allows to have much better observational characteristics. And the main, so okay, each pixel, so okay, this picture shows the camera with the shutter, and then all the wiring, all the cabling of the pixels. So there are 3,600 pixels in here with all the electronics readout, and this is one individual pixel. So this square here, so this is a G-APD with a solid light concentrator. So when the light hits this glass, so it's guided towards the area of the pixel of the G-APD. So it allows to reject all the, all the light that is like background light, to significantly reduce it and like concentrate it in one narrow spot. So, and voltage adapting, which is constantly used, so it allows to do observations even during the strong moonlight. So for other Cherenkov telescopes like HESS in Namibia or MAGIC on Canary Islands, this is impossible, mainly because the moonlight strongly interferes with the observations, so the electronics is not working properly. So PMTs, it's way too bright for that very sensitive sensors, while here with voltage adapting you can really observe even during moonlight. So why do you want to observe during moonlight? Yeah, because you have larger, wider data sets, a more complete data set, so you don't have gaps in the observations, which is not the case for HESS. So you have several days when the instrument is not operating, and if there is some interesting behavior in any object, you risk to miss it just because of moonlight. So here, FACT is able to monitor sources on a daily basis mainly without gaps. And so now I'm going to present about present you the structure of the data, of the HESS data. Let me check. Okay. Okay, yeah. Okay, I cannot access chat. So if you have questions, please ask me, just speak up, unmute your microphone and ask me, because I cannot, maybe when I'm sharing screen or it's something with the settings, but I just cannot open the Zoom window with the chat. So please, ask questions if you have one. So structure of FACT data. So the recorded data, so raw data, which is readout from the camera, consists of raw data, which is voltage curves for each pixel. So you can imagine these photosensors as just conversion of light to current. So Cherenkov light that is arriving to a photosensor. So it triggers current. So it's read out, and you have voltage depending on the time slice. So you've got during the pulse of Cherenkov light, you have different you have varying voltage. So this voltage versus time is the named voltage curve, and it characterizes the Cherenkov light pulse. We will talk about it later. And so this information is read out of each pixel, and then there is auxiliary data files. So this is necessary to interpret this raw data, because otherwise the pure value of this voltage, I don't know, it doesn't give you any information on the number of photons that you detect. And so the goal when you analyze data is you want to construct spectrum or light curve. So to know variability of the source, for instance, and flux distribution. And for that, you need to reconstruct energy of each individual gamma ray and its arrival direction. And you have to somehow come to these energy and arrival directions starting from the just voltage curves, so the varying current that you detect. So we will go through all this procedure during today's lecture. So the data is measured for this telescope. We measure data in certain time intervals named runs. So it's just a sequence. So no, it's a interval, typically 20 minutes for 28 minutes for Hess. So for fact, it is somewhat different. So runs, there are 3 types of runs. So there are pedestal runs, calibration runs. So these provide this auxiliary data, and data runs provide the information about the very high energy signal from the source. So, and one single sequence for fact comprises 4 data runs accompanied with pedestal and calibration runs. And what are exactly, so data run, okay, you can imagine it's more or less clear. We just focus on we point our telescope to a very high energy gamma ray source and just collect the signal. And to interpret this signal, we need 2 other runs. So pedestal run is measuring the night sky background, so NSB, and electronic noise. So you have the electronics itself, it has a noise, thermal motion of electrons and other noises. So calibration run is measuring actually response of each pixel. So what does it mean, response of each pixel? So when, for instance, 10 photons hit the G-APD cell, so it doesn't mean you will get exactly 10 photoelectrons. You may get 3 photoelectrons, and this response, in fact, is subject to variation, although I was talking about stable gain, etc. But still, we need to, each time we have to measure precisely what's this response of each pixel to ensure we are doing correct things. So, and measuring these response is actually allowing you to convert, so you get the number of photoelectrons, so you convert them back to what was the number of Cherenkov photons. So now about the pipeline for analysis of fact data. So why pipeline? So pipeline means that there is an individual step. So, and the first input is raw data, and then the output of each step serves as an input for the next step. So at the final output, you have your list of photons with energies in arrival directions, similar to one I was showing, you remember, for Fermi data. So essentially you had just list a table of events with the energy and arrival direction, which you only need for, which is the only information essentially you need for your analysis if you filter the data. So first you need to calibrate the raw data. So you need to go from the voltage curves, so pure electronic information, to photons, so Cherenkov photons. You need to know how many photons you got. Then you do the cleaning of the air shower image. Then you add auxiliary information needed to interpret the data, and you need to suppress the background, hadronic background and gamma-like background, and reconstruct your energy. So I'll go into detail for each step. I will sort out each step individually, so we will see what all that means. And final step is calculating the excess, which excess means the pure gamma rays from the very high energy source. So why excess? Well, because in fact, cosmic ray background. So when you observe gamma rays from your source, in fact, irrelevant of the direction where you're observing, you will always get the cosmic rays because they are isotropic, more or less. So they are incoming towards Earth from every direction on the sky with more or less constant rate and isotropic roughly. And typically the the number of events that so each of that particle falling, well, going towards Earth, it's inducing Cherenkov light. So air shower and the particles of the cascade emit Cherenkov light. So, and you observe, so each time telescope is observing, it's triggering Cherenkov light. So you both trigger events from the source, so gamma rays, which induce cascades and Cherenkov light. And so you also include Cherenkov flashes induced by cosmic rays. And the thing is that the number of air showers from cosmic rays outnumbers the number of gamma ray induced showers by 5 orders of magnitude, more or less. So you have way more background compared to the signal, and this is one of the unusual features for the Cherenkov astronomy. So we have to deal with that. We have to very precisely remove that background. And so the pure signal from the source is typically a tiny fraction, and that's why it's named excess. So it's excess over background. So first we start from calibrating the raw data. So we have our voltage curve. So we have some sort of shape over time. So current, and this information is provided for the 1,440 pixels of fact camera. And so to give you an idea about how fast is the electronics sampling the light. So total time window of the during which the event is recorded, so Cherenkov light flash, is 150 nanoseconds, and there are 300 time slices, which means that the sampling is done at a time step of 0.5 nanoseconds. So 1/2 of nanoseconds is impressive, right? So human eye can do only, so we've got 28, I think, FPS. So this is only 0.05 or something. So, and here is actually some 7 orders of magnitude faster. So, or something like this. So I would say this is really impressive. And why do we need these fast electronics? Because the flash of Cherenkov light that we capture is very fast. It's a few nanoseconds. And the timing of the shower allows you to, in fact, reconstruct better the particle that was causing the shower, like hadron or gamma ray. So what do we do first to calibrate our data? So yeah, just another note. So this pipeline will be somewhat different from HESS because, well, it's a single telescope. So you have different arrival direction reconstruction and different way how do you reconstruct energy as well. So in this way, you can see how the mono telescopes work. So yeah, so calibration. So to calibrate, we have 2 steps. One is pedestal subtraction, and second one is calculation of number of Cherenkov photons and their arrival time. So what is pedestal? In fact, exactly, this is a sort of, it's a sort of a constant shelf over which your voltage curve is rising. So it's an additional constant that is added to your voltage variations. So, and it contains information about NSB, so night sky background, and the electronic noise. So this is pure noise, and so it is measured with pedestal run. So how? So to measure electronic noise, so the shutters of the camera are closed. So this door, this is closed, and you have you measure pure electronic noise. So for a certain amount of time. So night sky background is actually removed later on. So, but if you measure, well, if you measure, it will be contained in the information. So when you will calibrate, you will see that there is an excess of certain pixels over the mean. So the night sky background will be removed later. So, and then this constant value with the noises subtracted from voltage curves when you left with pure Cherenkov signal. And so one important note is that, so here you measure the mean value of electronic noise and mean value of NSB. So keep that in mind, because during next step we will be removing the fluctuations of the night sky background and the electronic noise, which can be non-zero. So then we're left with pure Cherenkov light signal. So number of photoelectrons which were caused by only Cherenkov light and not by noise. And now we have somehow to convert it to number of Cherenkov photons. And this is where our calibration run is coming for help. So we need to convert this number to photons. So first we search for the time moment when the light curve is actually reaching maximum. So typically some sort of bump. So this will give you the approximate arrival time of photons to the pixel when the pulse arrived. And then, so you have to integrate this reduced light curve or voltage curve, yes. So the total integral will be proportional to the number of photoelectrons in the pixel and number of Cherenkov photons. But you need still to find your conversion constant. So you extract this conversion constant from the calibration run. So where you measured response of each pixels. So for that, how the calibration run is performed. So this is more or less the same for any Cherenkov array. So fact included. So the camera is illuminated with a homogeneous source. Let's say it's illuminated in a way with some sort of calibrated light source, artificial light source, which is illuminating every pixel homogeneously, more or less. And so we then what is measured, so the output from each pixels, how many photoelectrons. So, and we know, as it's a calibrated light source, we know what's the number of photons arriving in each pixel. Yeah, because we know the luminosity of our source, we know the distance, so we can precisely calculate that. And so we can, from that, we can extract the conversion constant. So as you see, the conversion constant is applied for 4 data runs. And then every 4 data runs, you remeasure your noise and your conversion constant. So, and this way you ensure that, well, the different observational conditions may impact that noise and conversion. So your electronics may be not very stable. So you ensure you are really adapting to the observational conditions, and you measure the response, well, you measure the number of photons right. So yeah, you apply it to the number of photoelectrons and you get the number of Cherenkov photons. So at the end of the result of the calibration, you are left with number of Cherenkov photons in each pixel and the arrival time. So what does this mean? So this means you have a sort of an image like this at the end index. So this is a camera view with 140 pixels. Okay. And for each you have the number of photons, so more or less intensity, and arrival time. So basically this gives you like a cartoon. So you can play this camera camera view over 300 time slices, and you can see how your air shower is developing. I would show you the animation, but I don't have access anymore to the tools. So as I left the collaboration, but okay, basically, so you can see how the shower is developing in time. So it's evolution. So you now see that there are some pixels, you see some blue pixels here and there. So it's not that homogeneous. So you need to do image cleaning. So to remove residual noise fluctuations and the NSB fluctuations. So not the night sky background itself, as we already have removed it, but the night sky background fluctuations. So you need to set certain thresholds. So 2 thresholds, so level 1 and level 2. So the highest threshold, level 1. So it's where you're selecting the core pixels. So you can already identify. So what is this actually? So this is actually the image of the air shower in the Cherenkov light. So, and this will give you the information about the, what do you want to learn from it eventually? You want to know the energy of the gamma ray that caused this air shower, and you need to know from where it arrived on the sky, right? So, and you can identify the core, like the brightest pixels, so with certain threshold. So it gives you this, it has a, for a gamma-like event, it has a form of like a sausage, like an ellipse, if you wish. So, and then level 2 is the pixels surrounding the core, and you require that they should be neighbors. So you, the pixels which are named used, so less bright, but the ones you assume should belong to this shower. So you are requiring they should be adjacent, so like a halo around your core, and everything that is not fulfilling that conditions is regarded as noise, as fluctuations, as well as garbage. So you have to filter that out. So anything that is lying outside of the island is also cut away, because you have significant constraints on the time evolution. So you cannot have really pixels which are far away and belonging to the shower, as it has a certain angular extent. So after image cleaning, you're left with the pure image of the shower, so more or less this shape. And okay, there are some other pixels which are, okay, somehow survived this procedure. And yeah, maybe it's just some residual noise, but yeah, this is your main image, and from here you have to convert it to energy and arrival direction. So how do we do that? So yes, so we calculate specific image parameters based on the geometry and the light content of the image. So we compute the following parameters, which are named Hillis parameters. So first parameter is size. So it's sum of signals of all shower pixels, and this correlates with energy. So okay, so you see these figures here. So you just routinely add all the values here. So here you have 22. So like this, you get the total number of Cherenkov photons in your air shower, okay? And it correlates with energy. And why so? Because, okay, because the number of Cherenkov photons you get from an air shower is proportional to the number of, sorry, to the energy of the particle that caused the shower. So you have this, because of this dependence. So obviously the flux of photons you get at the end is proportional to the energy, but you have to still find out that constant with which the correlation is happening. Then, okay, the number of islands. Okay, this is important for background rejection, because gamma rays typically give you very nice elliptical shape, while hadrons have higher, larger spatial extent due to the higher transverse momenta that particles get when during the interactions, and that that causes when you observe the hadronic shower, you have multiple islands in your image. So this allows you another way to distinguish between gamma rays and the noise. So length and width, so semi-major and semi-minor axis of the ellipse. So I will already jump to the image, which is illustrating that. So yeah, assume you have this air shower image, so you fit it with an ellipse, all right, based on certain threshold. And then you have number of islands, okay, obviously. Then the width is this semi-minor axis. Length is this semi-major axis. Yes, I said semi-major, so yeah, this and this, sorry. Then you've got the so-called disp. So disp is the distance between the center of gravity of the shower and the reconstructed source position. Okay, so assume you have your source here. good. So then you have the so the distance between this center of the image and yes, maybe I will first explain dist. So it's distance between the center of gravity of the shower and the true position of the observed source. So you know your coordinates of the source, you know it well. Where is it in the camera? So assume it here. So the dist, D-I-S-T, will be distance from here, from the center to here. And then how do you reconstruct the position of the source? The position of the source means here the arrival direction of the gamma ray. So you have your image. So obviously the shower will be elongated towards from where it arrived. So your major axis actually indicates a vector towards your source. So and it's calculated based on this, actually on this expression. So and sees a certain constant. So it's a peculiarity of the mono technique. So when you have one single telescope, so for multiple telescopes, so you have a different method. Maybe I can illustrate it. I don't have it in the slides, but okay, I can quickly show it. So open my PhD thesis and you can see, okay. Yeah. Yeah, good. So yeah, this is the method. How do you actually reconstruct the arrival direction when you have multiple telescopes? So imagine you've got 4 telescopes. So number 1, number 2, number 3. So they will be you will be seeing images arriving from different positions because they're located in different locations, and you superimpose them on one image, and you continue the the major axis, and they more or less intersect at one point, and that will be the yeah. And note this is the same gamma ray observed, but just seen at different angle, different views. So you superimpose them, and you see from where actually your gamma ray is arriving. Okay. So, and we go back to our slides. Yeah, so here you don't have any other telescope, so you just have one single line. So you just continue the major axis, and so your gamma ray is arriving somewhere from there. And the difference between the true source position, so which we are observing, and from where our gamma ray is arriving, so here is named theta parameter. So, and yeah, so this is more or less the deviation of the arrival direction from the source. So clearly the higher is theta, the more unlikely the event is to come from the source. And you cannot have, well, generally you cannot have the gamma ray arriving accurately from the source position because you have some PSF, so some response of the instrument. So you will anyway see, as I already was showing for Fermi. So here is a bit different story, but we still have some sort of PSF. So point source will be smeared into a sort of like some shape, okay, some halo. So we will need to impose some sort of cut, a threshold from where do we not accept any more events. So we regard it as not from the source. Now we go to the next step of our analysis pipeline. So hadronic background suppression and energy reconstruction. So first we sort out with hadronic background suppression. Okay, so what do? We need to filter out all that cosmic rays which are interfering with our observations. Once again, we've got like 5 or 6 orders of magnitude more. The rate of cosmic rays is some 5-6 order of magnitude higher. So imagine you've got few million of events in your sample you're analyzing, and among these million of events you will have maybe only 2 or 3 gamma rays, for instance. So you need to, as you see, it's very the analysis is it's very sensitive to how you remove the background which is dominating by many orders of magnitude. So first you have to remove anything that you cannot reconstruct accurately. So for instance, events that comprise less than 5 pixels, that will be very difficult to characterize. So we give up, we remove them. We have no other way to deal with them. So, and now the core, so background suppression cuts. So based on the parameters derived here, so there is a parameter named hadron likeliness, more or less in any analysis pipeline. So it characterizes what is the probability of this event being a gamma ray or a hadron, which will be 1 minus the gamma ray probability, okay? The similar one was for Fermi, but since a very different air shower, so not even air shower, but it's in a shower into a tracker. So, but they also had, so there are misclassified cosmic rays. But here we have only, we both have direct cosmic rays and then misclassified as well. So first we deal with cosmic rays observed Cherenkov light directly from cosmic rays. So we, based on the parameters, based on number of islands, based on the shape, so elliptical or more extended. So there are specific filter expressions which allow to remove events which look which are very likely looking like background, so cosmic rays. And then we have mostly gamma-like events, so gamma events, so events which are resembling to gamma. So, but still, going a bit ahead, we still have some sort of some fraction of events which are in fact misclassified cosmic rays, so which filter expressions were not able to detect. So which are more or less having the elliptical shape, but are in fact induced by cosmic rays. And I will explain how do we know that. So, and then we reconstruct the energy for every event. And okay, I will speak about it later on in the next step. So you obviously need to, so to reconstruct energy, as you know, so as the total light content, so parameter named size is correlating with energy, so you can already more or less guess the energy based on that, but it's not sufficient typically, and you need other parameters. So the final step of the analysis is calculation of excess, so the gamma ray events only from the observed source. So yeah, just in case, so here I'm talking about the point source. So gamma-like background. So the observational strategy of FACT telescope or even HESS. So the telescope is monitoring the source more or less in the center of the field of view, and then the telescope is moved, its direction, observational direction is shifted a couple of degrees left or right aside, so with more or less, so around a circle, so to probe background around the source. So you measure, so which background exactly as you filter out hadrons. So the misclassified cosmic rays. So if you observe aside, and even if you apply this background suppression cuts, you will be not left with nothing. You will have still some events which look like gammas, but you don't have any sources from there. So what's the reason? The reason is that still our filter, let's say our filter is not sufficiently fine enough to filter out all the cosmic rays. So there will be events which look like gamma rays, but are induced by cosmic rays. So, and that, so when doing this wobbling strategy, so when observing aside from the source, this gamma-like background is measured, and then we subtract we subtract from when we observe in the source region. So we have, what do we have there? We have source counts and the misclassified gamma ray counts, so gamma-like background. And we subtract from the source observational counts, we subtract what we observed aside from the source, so pure background gamma-like, and we are left with only with pure gamma rays. But the thing is that there are residual events which might be not coming from the observed source, so too far from the source accidentally. So we have to remove them as well. And so how do we do that? So a so-called theta square cut is applied. So anything too far from the source is removed. So this is example of a threshold used in the analysis. So theta square less than 0.1 or 0.11, okay. And this plot illustrates this cut. So you can see how is it selected, why this value. So this value is selected on the basis of, so this is the number of counts distributed over the square of this distance between the true source position where the source is located and from where our event is coming. So these events come really close from the source, and these events come far from the source. So obviously they don't belong, but where is the transitional, how do we set our threshold? So more or less when the red curve meets the blue curve, so the red curve is for the background and blue is for the source, I think. And so it's more or less where you see 0.11 is somewhere here. It's more or less where we really remove all the possible background. So beyond, so what is beyond? So beyond 0.11, so this tail, so these events are associated with residual events. So, and here, the success here is this is the source. The red is the source counts. So here you have your contribution from the source, which is, you see, is sharply decreasing, and then it's just on the same level as the background. So like this, we cut, and we are left only with the source events, and nothing is no background tail. And after this procedure, we have only gamma ray events from the observed source. So we have only good events, and then we have reconstructed energy for each of them and the arrival direction. So we have a list of photons, and we are ready to construct light curves and spectra. So, and I wanted to say something. Okay, maybe it will come later. Okay, so yeah, now how do we actually can reconstruct the energy starting from the shower, from the image of the shower, and other parameter you need to take into account. So if you want to compute physical flux, you need to know more or less the collection area, so the effective area of your instruments with which the gamma rays can be collected. So here, how do you, so for that, it was more obvious because you had 1 meter by 1 meter by 1 meter, but 1 meter by 1 meter, sorry, and you had some dependence with energy. So depending on the angle or depending on the energy of the gamma ray, so for some energies, your instrument is less sensitive. Here is the same. So your instrument, actually one instrument, but typically one gamma ray or any other particle is inducing shower with the light pool. So the Cherenkov light is distributed over a spot on the Earth of roughly 120 meters. So if you're lucky if your telescope is lucky to be in this pool, so you will be seeing the light, so you will see the event. So this yields you huge collection areas. But in fact, it depends on the energy of the gamma ray and what's the inclination, so which angle is the event, is the gamma ray is arriving. So you will have very different results. So you need to compute that. And how do you compute that? Two things. energy reconstruction and the effective area. So for that, you need Monte Carlo simulations. And I don't know if you're familiar with this, well, what are Monte Carlo simulations, but in fact, it's just simulation of random processes where you generate fake data. So it's kind of experimental computing. So, and yeah, it's named after Monte Carlo, after a casino in Monte Carlo. So many randomly gambling. Okay, I will not go into full story, but so this is example of Monte Carlo simulations. So where so the cascades of particles. So you have when particle is interacting with medium and the secondary particles are interacting with the medium, these processes are random in nature. So there is a certain probability of interaction, and these are characterized with cross sections and mean free path. So and okay, in interaction, okay, if you have 1 kilometer mean free path for some particle, it doesn't mean that 1 kilometer it runs 1 kilometer and then boom, it interacts and other particle is created. So it can be around 1 kilometer. So it's random in nature. So you have many different random quantities involved. So it's very difficult to compute analytically, if possible. So for that, so in the given example of air shower, you've got particles which are, you simulate. So you have, your input is, for instance, 1 gamma ray with a given energy, and then you run over many instances. So you simulate how the interaction is going on and with different random numbers. So one case, second case, and you have 10,000 or hundreds thousands of the showers, and all of them have somewhat different. So you will have different different propagation path for particles. And then from that, what do you want to know? You compute some average characteristics, or you construct the distributions. So all of that is very tricky to do analytically. So you do it computationally. So this is example of the Monte Carlo simulations for gamma ray showers. So this is how, so there is a gamma ray and these are secondary particles. So this is their extent in the atmosphere. And the hadronic shower, so you have, for instance, cosmic ray proton, and these are the secondary particles. So this is some sort of average image for their propagation, or one example, I don't know exactly. So you see hadronic showers, they have much higher extent and there are multiple islands. And this is one of the way, how do you filter them out? So the Cherenkov image, so all these particles give you Cherenkov light, which is superimposed together, and you see quite a different picture from two of them. So yeah, so you need to simulate these showers to be able to reconstruct these quantities, to compute these quantities. So let me start first from energy reconstruction. So how do we measure the energy of a gamma ray? We have the image like this. Yeah, and how do we measure energy from this image? So for that we need Monte Carlo simulations. So we know already that the total light content is correlating with energy, but we need more. We need a precise rule how to convert the image parameters to energy. So we need to simulate the effect data. So we simulate many air showers like this, yeah, with different energies, with different parameters like zenith angle, you know, different characteristics. And okay, you know, fact electronics, it has certain response to the Cherenkov light. So there are certain detector simulations, so which is quantifying the response. So you actually simulate the whole observational process. So you generate many events like these. You convolve them with the response of fact. So you obtain, as a result, you obtain the basically the raw data, the fake raw data, how FACT would see the simulated events. Okay, and then you just apply the whole pipeline I was presenting to you just a few minutes ago, the whole data analysis pipeline to these simulated events. And you get your artificial images, right? And you get your image parameters. So, and from here you can already try to estimate that conversion rule. So you have you precisely know the energies because you input them by hand, 1 TV, 2 TV event, and you have your image parameters. So which are output values. So, and you assume some analytical formula. So as I said, the energy is linked definitely to the parameter named size, which is total light content, and maybe other parameters. You can already guess that probably the inclination angle, so how the gamma ray is arriving, to which angle it's arriving towards your detector, will impact, because the Cherenkov light is very concentrated in a cone of 1 degree or more or less. So if you're beyond that 1 degree, you receive few photons. So you definitely need that to include as well. And so you assume some parametric function that links your energy with image parameters, with parameters P1, P2, and so of course you have your energies you input by hand, and you apply this formula. This will be reconstructed energy, and you feed these parameters P1, P2 to achieve a good agreement between the energy which you input and the value which you reconstruct based on the shower image parameters. Once you get your energy estimation formula, you apply it to all the events from the real data to reconstruct what is their energy. So this is an example. So the work which I did during my master thesis, like 4 or 3 years ago. So I was simulating FACT data, so simulating events and how FACT would see them, applying all the data processing. And so the example of a typical dependence which was used, so as energy correlates with the number of the Cherenkov photons, so it will be proportional to the size and with some power. Let's say we assume some power alpha, which should be close to 1. And as I was talking about the angular extent, so it is also should be proportional more or less to 10 in the power of some polynomial function of parameter dist. Let's go quickly and see again what is this value. So dist is the distance between the shower image center and the true source position. So it will be more or less will characterize you the inclination angle, right? So the further is your event from the source, so the less Cherenkov photons you get. So to convert back from so here you have another task. So you have a number of Cherenkov photons, and you go back to the initial number of Cherenkov photons contained in the entire shower. So you multiply back by this, so it is maybe exponential profile or something like this, or power law profile. So you go back to the total number of the photons in the shower. So, and this is really linked to the energy. Maybe there is a coefficient here as well. So you tune these parameters like alpha, parameters of polynomial, and the constant here, which I didn't put. So, and then what do you have to achieve? You have to achieve a good agreement between the true value of the energy which you put into simulations here. So you have some distribution. You see 1 TV, 10 TV, 1.5 TV, and so these events are processed, and you have parameters which you put in here, and you get your estimated energy or reconstructed energy. And so we plot it here, and so you have to get a good agreement between them. So this plot shows you that there is a very good agreement for this particular expression. So so this is logarithm, so this is 1 TeV, so logarithm of energy in GeV, so 3 is 10 to 3 GeV, so 1 TeV, 10 TeV, 100 TeV. So in the entire range, you can see that the true energy will be, so the reconstructed energy will be close to the true energy with a certain, okay, with a certain error, of course, so you have some uncertainty. So for some events, you reconstruct not very precisely. So you have true energy of 100, maybe 10 TeV, but for small fraction of events, you will reconstruct a bit lower energy or a bit higher. But for most events, you reconstruct an energy precisely. So the goal is to find from Monte Carlo simulations these relations so that you know you reconstruct your energy very well. And these extend the uncertainty you include in the final error on the flux. So second reason you need the Monte Carlo simulations is effective area. So you need to know what's the effective surface of your detector versus energy. So Monte Carlo simulations help to estimate that as well. So again, you simulate events, but now with different impact parameters. So what is impact parameters is how far is your event hitting the ground, or let's say the shower axis. What's the distance between the shower axis and the axis of Cherenkov telescope? So it can be, I don't know, 0 meters, 10 meters, 50 meters, 200 meters. So typically beyond 400 meters, you won't see any photons, as the Cherenkov light is very concentrated towards ground. So you calculate, so you do the processing and you see how much events, so the fraction of all your simulated events, so how many of them remains after trigger and cuts. So this will give you the more or less, you see, so this will give you the fraction of events that the detector can see, and the fraction of events that survive your analysis filtering. Then, so this will be the effective, this will be defining the effective area. And you multiply this fraction by the geometrical area of the total surface in which you simulate it. For instance, 400 meters by 400 meter circle. And so this fraction, you multiply it by geometric area, and it will be the effective area with which your detector is capturing the events, so these events which are remaining. So it's very straightforward method, and the result, so again, this is my results from master thesis some 3 years ago, and this is the effective area versus the energy divided by 1 GeV logarithm. So 3 is 1 TeV, 4 is 10 TeV, okay. And blue and black dots, okay, these are details, but just you know, if you're curious, so these are for 2 different detector simulations. So there was a change in the detector before May 2014, so then the effective area was slightly changed. Anyway, so it's rising more or less and saturating at around 1 TeV, and then is somewhat constant. So the effective area reaches around, you see, 10 to 9 centimeters square, which is very impressive for a standalone single telescope. And you see near 100 or 400 GeV, it's rapidly, sharply declining, so you won't see any events with small, at low energies. Why so, you may ask, but the question is very, well, the answer is very straightforward. So because very low energy events, they generate very few Cherenkov photons. Once again, the number of photons is proportional to the event energy. So if you have very few events, this will trigger very weak response from the detector. So you will be actually very marginally detecting it over the noises. So that's why it's reflected in the effective area. Good. And so now the final thing for today is the how do we actually select the data from FACT. So I was talking about the pipeline and how do we reconstruct energy and how do we compute effective area, but we are not actually uh, when we are analyzing specific source data, we don't want to, we want to include as much statistics as possible. We want to have as much data for higher quality spectra. We want to have more data to have more sensitivity, to see fine details in the behavior, but we have to exclude certain data because it might be bad. The same as for FACT, same for Fermi LAT. I was talking before, but here, okay, it's a ground-based instrument, so you have a different way to perform the data selection. So what can interfere with your observations? So as I said, FACT is observing on night-by-night basis, and it's tracking given set of sources. And okay, it's a ground-based instrument and uses atmosphere as a detection medium. Okay, so any perturbations in the atmosphere will affect the data quality. So what can affect its data quality? So for instance, bad weather, if you have clouds, so obviously clouds attenuate the Cherenkov light. So you have fewer Cherenkov photons, and you are mistaken when reconstructing the energy. You may think that the energy is lower. So you will have completely wrong data and wrong spectra. Then you might have ambient light interfering, so moon or car flashes. So, okay, why car flashes near an instrument? Yeah, it's a particular problem for FACT because it's located, so Canary Island, so the instrument is located on more or less on, it's this Canary Island is like a mountain, and its elevation is, I don't remember, maybe 2,000 meters, something like this, above the sea level. And okay, you need obviously to deliver things towards the observational site, there is a shifter change, and so the only way to get there is by car. So there is I never been there on site, but this is what I heard from people. So people are going up the serpentine slope, the road. So it's a winding road toward the site, and okay, there is no illumination to don't have, so you don't have any noise. So you can only drive with the light, with the headlights on. So it's not recommended to do it during observations. They try to avoid it, but sometimes it's difficult to avoid. So occasional cars that are passing by, going towards site or from site with their headlights on, which is reflected from the surroundings, so it can be actually interfering with the observations, right? And there is another attenuating entity, so the so-called Kalima, which is the dust wind. So Canary Islands are actually located not that far from Sahara Desert, and the wind, the strong wind, can blow this sand from the Sahara Desert towards towards Atlantic Ocean, and these sand passing through, may pass through the Canary Islands, so above at certain altitude above. So this is called Kalima, and this strongly interferes with the observations, again, as it's scattering light and absorbing partially. So you will have poorer quality of your data, and you have to actually remove this data during the bad observational conditions. Otherwise, you will have completely wrong results. So how do you achieve that? So one of the ways, so for single telescope, it's a strategy for a single telescope like FACT. So you've got your trigger rate. So what is the trigger rate? So the rate, the number of events per unit of time you detect. So real-time analysis, usually when you're observing, so you're monitoring the conditions, and so you know more or less how much Cherenkov light events you detect per unit of time. So it is actually varying, but varying in near some constant level. But if you can see that it's strongly deviating, then it might be a hint that you have your something interfering with the observations. Then there is a rate of gamma-like background events. So it's also supposed to be more or less constant near one source. But if you have clouds, for instance, then you have fewer photons, so you see it as fewer events coming. So you use these two quantities. So let's say background rates. If you see you have fewer background, then it means that you have problems with your observations. So something is affecting your data. So so these both quantities, they're linked to the cosmic ray rate. So the rate at which cosmic rays are reaching the surface of the Earth, and it's quite stable. So deviations from this constant are due to some conditions which are interfering, and you can use to select data. So so first we can calculate the so-called artificial trigger rate. So it's the cosmic ray which we retrieve from the data run. So the data run, so all the events are before the background filtering. So most of them will be just cosmic ray and light curve of gamma-like background. So after background, so hadron background suppression cuts, but before subtraction of gamma-like background. Or the most precise way to achieve, to compute it is basically just to look at the off fronts, so off oval positions. So it's when you're measuring background away from the source, so misclassified gamma rays or residual cosmic ray. So in these two quantities, you can plot them and see if there are any variations. So again, if you have clouds, then you will have fewer photons and you will see it as fewer, so lower rate of the background of the cosmic rays. If you have car flashes, for instance, or moon, so okay, let's see separately. So car flashes, you see more light, so you may you see it as higher rate. So increase of rate, it's maybe due to stars or car flashes. Then if you have moonlight, so you adapt your trigger threshold. So in order to remove the night sky background or any background noise, any background light. So there is a so-called trigger threshold. So trigger rate is defined by this threshold, okay? And the more, let's say you want to detect some number of Cherenkov photons over the background. So the more background you have, so you have to raise your threshold to filter out this. So what's the rule for Poisson statistics? So you have the fluctuation, more or less the error, the fluctuation will be square root of the number of background photons. So if you have, okay, you have, for instance, you measure 100 photons background, so it will be fluctuating with square root of that, so 100 plus minus 10. So and you have your number of Cherenkov photons in the shower should be higher than these fluctuations, so 10 photons. So you set your threshold to 10 photons, and then if you have more photons than that, you capture that event and record. You have 8 Cherenkov photons, you're not sure, maybe it's due to the fluctuation of the background. So you remove that to not confuse with just with the statistical fluctuations. So if you have more background light, you see, so you, for instance, not 100 of photons, but 200 photons, you have more, you have something like 14 fluctuation is more or less 14 events. So you have to increase, you have no way but increase your trigger threshold. So only trigger events, Cherenkov events, which have more than not 10, but now 14 photons. And like this, what happens is that you miss many events with lower energies, again, proportional to the energy, right? So you miss a lot of events with low energy. So you discard, the more you raise your threshold, the more events you discard. So this will result in decrease of your rate. So strong moonlight will lead to decrease of the trigger rate. And so the Kalima, again, it will be, again, decreasing number of photons, so decreasing the rate. So you can more or less guess. So if the rate is increasing, then these are most likely car flashes or stars in the field of view. if it's decreasing, then these are clouds, or these are kalima, or this is moonlight. But the moonlight, so these are transient events, right? Most of them, but moonlight is more persistent, okay? And you can, for clouds or for kalima, for the moonlight, okay, this information is available. Just check the weather or check the moon phase, so you can already associate. Car flashes are a bit more tricky, but to be safe, you just filter out all the data which was taken during when the trigger rate was very high. So an example of this data selection. So this is the last slide. So how do we do the data selection? So you, again, this was the algorithm I developed during my master, and it's one of the possible methods. So it's not really don't think it's a solid single method. So it's one of the approaches, but most of the data selection is in Cherenkov astronomy is using that in one or another way. So as I said, so we're using backgrounds. So the left plot is showing the artificial trigger rate, so cosmic ray rate, retrieved from the data, and the gamma-like background, so what you observe aside from the source in wobble positions. And you see they're really messy. So there are drops in here, there are increases, so maybe car flashes, maybe, so where you have constant decrease, maybe moon, and where you have occasional decreases, this might be cloudy weather. Anyway, you don't want, so you can see there is a lot of conditions which were interfering with observations. You really don't want the data from during the days when when you had problems with your rates, or when you had something deviating from a constant level. So this data is obviously wrong. So what do we do? So what I did, so the goal is to choose levels, choose 2 levels to filter out most of these outliers. And obviously you don't want it to lose, because you want good statistics, you want enough data. And we allow 10% on uncertainty in the level of the rates. So level of the rates, so we want to have more data, so we allow, because okay, the trigger rate, maybe it can fluctuate. Well, we want more data, and so even if there are observational conditions which are only slightly affecting, like very moderate clouds, so we still want the data to include, and it will be wrong by 10%. Okay, and we can include that in our final uncertainty of the flux. So we want more data. We want more events to have higher quality spectra, for instance, but we're okay. We say, okay, 10% of uncertainty, but our spectrum will be extending further in energy. For instance, if we apply loser cuts on this selection. So yeah, so this is how the selection looks like. So level 1, level 2, and we select all the events. So this is the way, in a way similar to GTIs in LAT, so good time intervals in Fermi-LAT. So we set these 2, you see, 2 levels, and everything, all the observational times between these 2 levels will be the good time intervals. So when we had no or very minor up to 10% problems with our observationals, when our data is valid and correct. And so these good time intervals, so we select data only from these good time intervals and apply the whole pipeline I was presenting you. Reconstruct energy, reconstruct arrival direction, we have our photon list, and then yeah, we construct spectra, we construct light curves, and perform modeling or interpretation of these results, and we can say something about the source. So this is it for today. And do you have any questions? So you can ask, just unmute your mic and you can say something. Okay, seems like there are no questions. Okay, I can stop sharing. And okay, so thanks for your attention. And by the way, some good news. So I finally got my visa for South Africa a few days ago. So I'm arriving to Potch on May 29. So maybe see you, yeah, end of May, beginning of June. And yeah, I think that's it for today. I can